Hi everybody, how's everybody doing today? Feeling good? Trying to stay out of the heat? It's much nicer in the studio here. It's very cool. Thanks for the air conditioning, Dave. Appreciate it.
We paid our taxes.
These guys paid our taxes. Yeah. How's everybody feeling about this stuff? Are you feeling a little overwhelmed these days? Okay, good. That means you're paying attention. You're in the right spot. Okay, this stuff is very challenging. It should be very time-consuming, and just do your best to absorb as much material as you can. The point of this couple of chapters that we've been dealing with is the idea that changing one field affects other fields. Okay, so changing the magnetic field led to a changing of some sort of electric field. We called it the EMF, right? The electromotive force or a voltage. But it's this idea that these things are actually going to talk to each other. Okay, and so this is where we're heading. The next topic, therefore, is just that, electromagnetic waves. Okay, we are now going to combine both of these things, electricity and magnetism, into one concept, electromagnetic waves. So let's talk for a second about the following. Let's say we have a charge, positive charge, and we have a negative charge. And let's say we're going to take these two charges and we're going to move them up and down. Okay? So let's move them vertically. And let's see what happens as a function of time. Well, at one instant at time, they look like that. And if I think about the electric field in between these two, I know what the electric field looks like. It's pointing from the positive to the negative. Okay, I'm just going to draw one line for simplicity. But now let's move them vertically. So the plus is going to come down, the negative is going to come up. And so at some later time, they're nearly right on top of each other. And at that time, the E field is essentially zero. Okay, there's nowhere I can draw an E field very cleanly. But now let's keep moving them. We're going to put the positive charge all the way down on the bottom and put the negative charge up on the top. And now the E field is pointing up. Okay, so all we're doing is we're taking these positive charges and negative charges, we're putting them together, and then we're going to keep moving them. So now they're the opposite way, and then we're going to come back together again. So now the minus is heading back down, and the positive is heading back up, and eventually they're back to where they started. So if I think about what this E field looks like, it is getting smaller and smaller and eventually zero. And then it flips direction and starts getting bigger and bigger, and now it's a positive. And then it gets smaller and smaller until it's zero, and then it flips direction and gets bigger and bigger until it's again pointing in the negative direction. It sort of oscillates up and down. Okay? And that hopefully looks familiar to you. Right? We like things that oscillate. And if I think about drawing the electric field as a function of time now, what can I say? Well, here it was negative, so it's some negative value. Here it was zero. Here it was positive. Here it was zero. Here it was negative. And so it's going to look something like this. Okay, it oscillates up and down as a function of time. As I move these charges up and down, the electric field is going to oscillate up and down. It's pointing down here. And then it's pointing up here. And then it's pointing down over here. And so forth. A graph like this is just what is the size of the electric field as a function of time. So here, the electric field is zero. Here, the electric field is zero. But at this point, it's a positive number. At this point, it's a negative number. All right, let's go back to this picture here for a second, and let's think about this charge. Okay, charge moving up and down, that is a lot like a current. If I take a wire and I run current up and down, then this current I would look like positive charge heading down and negative charge heading up. These are equivalent pictures. But we know what happens when we have current. What happens when we have current? What do we generate when we have current in a wire? It was the title of a couple chapters ago. Magnetic fields, right? If we have current, we have magnetic fields. I leads to magnetic fields B. And so there is a magnetic field that develops here. How does it develop? Like that. Okay, and you can pick the direction based on the right-hand rule. Remember, you put your thumb in the direction of the current. So stick your thumb down in the direction of the current. Your fingers are going to wrap around in the direction of B. Okay? And so we get a B field that looks like that for this particular picture. That was this case. But when those charges come together, now the current is equal to 0. And if the current is equal to 0, then B is equal to 0. And later on, as we keep going, the current's going to change direction. The current is going to be going up later on. And if current is going up, we again develop a B field, and you use your right-hand rule, and now it's wrapping around this way. Okay, thumb in the direction of the current, fingers are wrapping around in the direction of the B field. Okay, again, it's going to be confusing if you look at me in the glass here, so look at the computer monitor when I do this, and confirm that your thumb going up gets you a B field that wraps around like that. Okay, and when you do it in the monitor, make sure you use your right hand. Does everybody see that one? Okay, so the charges went up and down. We developed an E that oscillated in time. But now we have a current that's going up and down, and we're going to develop a B that oscillates in time. And so if we draw B as a function of time, it is going into and out of the screen. If I think about just one side of this, B is now going to be like this. Okay, and this is supposed to be coming out of the screen and into the screen over and over again. And we're trying to draw it in the third dimension here. So the E field was going up and down, but the B field is orthogonal to that. It is 90 degrees to that. So if the B field's in the plane of the screen, then if the E field is in the plane of the screen, then the B field is in and out of the board. All right. But maybe we can put all this stuff together. So the idea is this. A changing E generates a B. And a changing B generates an E. I change B, I can generate E. But if I change E, I can generate B. And maybe these things can balance out just right that you can generate electromagnetic waves, and that is indeed what happens. Okay? An electromagnetic wave looks like this. I've got an E field that is going up and down, like so. And this means that it's pointing up in this region. And then it's pointing down in this region, and so forth. Up, goes through 0, pointing down, and just keeps oscillating back and forth. But that changing E field can generate a changing B field. And the B field is orthogonal to that. It's at a 90-degree angle to it. So if E is up and down in the plane of the board, then B is in fact going in and out of the board. And this is a little hard to draw, but the idea is B is pointing this way, and then it's pointing into the board, and then it's pointing out of the board, and then into the board, and so on. Okay. So these things are doing something like this. E field is going up and down. B field is going in and out. And so they're sort of doing this. Okay, it's like two fish swimming along. One going up and down, one going left and right. And as this happens, this entire thing propagates to the right. So, what is weird about this? What's weird about this is there's no charges anymore. There's no wires of current anymore. These things can just propagate on their own because the changing E field creates a B field, changing B field creates an E field, and they just keep going like that, sloshing back and forth. And this is called an electromagnetic wave. So, how fast do these things propagate? We said that it's going to propagate to the right. It is called a transverse wave because the E field and the B field are perpendicular to the propagation direction. Okay, so even though the wave is moving this way, the E field is oscillating up and down. The B field is oscillating in and out. Those are both perpendicular to the propagation direction. How fast are these things moving? How fast does an electromagnetic wave propagate? Well, I think we know the answer to that, right? They propagate at the speed of light. 3 times 10 to the 8th meters per second. So this stuff, electromagnetic waves, came about from something called Maxwell's equations. And up until Maxwell, we had independent quantities. We had electricity, and then we had magnetism. Electricity was governed by things like Coulomb's law. Magnetism was governed by things called Ampere's law. Faraday's law started to tie those two together, but it wasn't until Maxwell came along and combined all of those things into one quantity that we ended up knowing that light itself is made up of electromagnetic waves. People knew a whole bunch about light. People knew a whole bunch about electricity and magnetism, but what they didn't know was that light itself was electromagnetic waves. And Maxwell put all those equations together, combined them into 4 neat equations. And if you happen to continue in physics and take my upper division, electricity and magnetism course, it's all about Maxwell's equations. Start with those 4 equations and spend an entire year trying to uncover all their interesting phenomena. Okay, it's really very fascinating stuff. All right.